Hello, everybody. Welcome to this webinar on how to improve resolution. We all face challenges to separate compounds as good as possible whilst doing our preparative chromatography. And in this webinar, we will learn more about how to improve resolution and fractionate our compounds more efficiently. First, I'd like to introduce myself. My name is Peter Neff. I'm a global application specialist for chromatography at Büchi, and I am part of the Pharma and Chemistry department, which offers laboratory and industrial evaporation equipment, spray dryers, melting point units, and preparative chromatography solutions to R&D labs worldwide. I am mainly responsible for the pure chromatography units, which can be seen in the bottom right of this slide. In this webinar, I want to touch on the basics of chromatography. Then I would like to show you what parameters resolution is made up of and how to optimize it. And finally, I would like to give you some tips and tricks on how to better separate your compounds. A chromatography instrument comprises of a mobile phase reservoir, a pump to flow the mobile phase through the system, a sample injection device to load the sample on the column. This is where the actual separation happens. Then a detector, which is linked to a recording device, which is in most cases a computer, to measure the changes in the composition of the eluent. And finally, a fraction collector allowing separate collection of the fractions with the different compounds. Now, important for the separation is the separation does not take place in the instrument, it takes place in the column. The instrument only controls the condition inside the column, and this is very important to know and to remember. Chromatographic separation is based on a balanced state among the compounds to be separated and an absorption agent in the column, which we in most cases call stationary phase. And also with the solvent flowing through it, and this we call the mobile phase. When a compound settles on the stationary phase, this is defined as absorption, while the detachment into the mobile phase is defined as desorption. So a high absorption capacity between the compounds of interest and the stationary phase means that there is a higher retention of these compounds and that there is a considerable delay in the elution from the column. The separation of a mixture into its individual components is only possible if the individual components in a combination of stationary and mobile phase have different absorption and desorption properties. Most flash chromatography and HPLC is performed using either normal phase or reverse phase methodology. The differences between these methodologies lies in the stationary phase chemistry and the solvents used to separate a mixture's compounds. The elution sequence of the compounds eluting from the column are opposite according to the methodology used. So in the next few slides, we will look into closer details of how both methodologies are made up of. The polar properties of a sample or compound to be separated direct the choice of the absorbing material. The most appropriate stationary phase as well as satisfying mobile phase should be identified by means of small-scale runs on analytical TLC. This method does not require too much time, is relatively cheap, and consumes very little of the sample. So TLC plates can usually be found with the same absorbent as the column filling material. Chromatographic separations with the normal phase which is more polar than the solvents, are considered as normal absorption chromatography. Silica with various porosities and particle sizes is the most widely used absorbent for this purpose and should be used first in choice for test runs. In some cases, aluminum oxide or for special purposes also polyamides are used. They are also considered more as normal phase stationary phases. In absorption chromatography, the strength of the mobile phase or the solvent is determined with the elution time. The solvent strength is a property of displacing a substance from the active side of the stationary phase. In the case of alkane, for example, the property is very weak, while in the case of methanol, it is very high. In this sense, solvents are described as weak or strong. If the solvents are arranged in order of increasing strength, a so-called allotropic series is obtained. Apart from the strength, however, there are also other factors that affect it. Such specific properties are the dipole parameter, the proton donor parameter, the proton acceptor parameter, all of these. But that is too much detail for now. So in summary, it can therefore be stated that the solvent strength determines the elution time, whereas the other parameters listed determine the selectivity of the solvent. These circumstances should be taken into account appropriately when choosing the mobile phase or its composition. Only a single mobile phase with a strength and selectivity adapted to a particular separation problem gives the desired success. So in the table, you can see an overview of the most commonly used solvents. The most standard solvent pair used in mobile phase separations are hexane and ethyl acetate. Currently, there is a trend of using heptane instead of hexane due to the lower health risk. DCM and methanol is also a very common solvent system, but used mostly for organic compounds with highly polar groups. For other more hydrophobic sample types, such as peptides, reverse phase chromatography is the method of choice with a C18 silica. In the contrast to normal phase absorption chromatography, in reverse phase chromatography, the stationary phase is less polar than the mobile phase. Hence, the situation is exactly reversed. That is also that the compounds elute opposite to normal phase chromatography. As mentioned before, everything takes place in the opposite sense in reverse phase chromatography compared to normal phase chromatography. This also applies to the mobile phase. Water becomes the weakest eluent and the solvent strength parameter increases with decreasing polarity. In reverse phase chromatography, the mobile phase generally used are mixtures of water and a second water miscible solvent. The most commonly used solvents are water-methanol mixtures because of the decreasing proton donor parameter, water acetonitrile. However, the high toxicity of acetonitrile should be noted. So for choosing the solvents, a balance between the following parameters has to be done: toxicity, cost, and also viscosity. From a chemical point of view, silica gel consists of silicon atoms, which are linked by oxygen atoms to form a three-dimensional network. The individual silica gel particle is a porous structure in which the terminal silicon atom are unsaturated with OH groups. They're also called silanol groups. This is the case over the entire surface of each pore. The stationary phases used are chemically modified silicas. The reverse phase packings share very similar, if not identical, characteristics with the normal phase silica gels. In these substances, non-polar organic groups, in general C18 or C8 radicals, are bonded to the silanol groups of the silica gel. The bonding takes place via a very stable silica oxygen-carbon bond. In addition to the groups mentioned, which are the most common ones, other modified phases are also obtainable. For example, those possessing phenyl or cyclohexane groups. In these phases, the interactions take place between the hydrophobic part of the molecule and the non-polar group of the stationary phase. Some of the advantages of normal phase chromatography are the sample can be dissolved in a non-polar solvent. It can be used for analytes that may also decompose in water. It is good for separating isomers and very hydrophobic or hydrophilic analysis. It can be used, or it can use higher flow rates due to the low viscosity of the solvent. Moreover, the solvent can easily be evaporated in a rotovapor, as the solvent typically have very low boiling points. Some of the disadvantages of normal phase are high cost for purchasing and disposal of solvents, and difficulty controlling the solvent strength. Retention may be variable, and gradient elution can also be difficult because of water uptake in the silica columns. Compared to normal phase chromatography, it is a very economical method. Moreover, the cartridges can be used multiple times if cleaned and also stored correctly. The disadvantage is the cartridges are more expensive because the stationary phase has to be modified. But I think the ability to use the cartridges multiple times makes the cost of both techniques around equal. Another thing that is very often forgotten is the back pressure of water and organic solvent mixtures, because they have very high viscosities. And this reflects highly in the back pressure phase during the separation. In many cases, the flow rate has to be reduced due to the limitations of the hardware, especially the cartridge. Now, regardless of normal or reverse phase, the resolution is important for both methodologies. The resolution describes the relative position of two peaks. Since also in this case, material-specific factors and factors relating to the apparatus play an important role, the precise test conditions and the exact definition of the absorbent must always be given. The resolution, which you can say R, is a very specific characteristic. It is suitable for comparison purpose when only one absorbent of a defined test mixture are used in the laboratory. An optimum time-benefit ratio is obtained with a resolution factor of 1. Now the equation to determine the resolution is seen on the top of the slide. It is made up of 3 factors, also described as equations in the bottom. They are retention factor as factor K, selectivity as factor alpha, and finally the efficiency factor M. We will discuss how they come together in the next few slides. The parameter selectivity has the highest impact and is highly dependent on the molecules to separate, the mobile phase used and also the stationary phase. So in the end, The parameter you can tweak here are the latter two. The selectivity describes how two molecules elute in the chromatography run. Selectivity is relatively easy to alter, with the mobile phase composition and the stationary phase being the primary means of adjustment. The hydrophobicity, polarity, and nature of the chosen stationary phase all play a crucial role in analyte interaction and directly affects the selectivity of the separation. When choosing the stationary phase, you should keep in mind the basic rule, like for like. In other words, you should choose the stationary phase with similar polarity characteristics to those of the sample components. For example, higher polarity of the stationary phase will increase the selectivity of the cartridge for the polar components in the sample. But when the solvent modifications don't help on a seemingly adequate phase, the only solution is mostly to go for another stationary phase. And as we learned before about the stationary phases, silica has a high polar surface. It is the most popular stationary phase, ideal for conventional applications. C18 has a non-polar surface, ideal for peptides and proteins. Amino has a medium polar surface, ideal for carbohydrates, nitrogen-containing compounds, and amines. Diol has a low polar surface, and this is ideal for lipids. And aluminum has a high polar surface, ideal for acid-sensitive compounds. Another aid in the optimization of the mobile phase is the selectivity triangle worked out by Snyder. In this connection, the common solvents were divided into 8 selectivity groups according to their resultant selective properties. And these groups were arranged in a triangle, the corners of which indicate dipole or proton acceptor and proton donor properties. Thus, we have a very clear representation of the solvent properties. In this case too, however, there is still the problem of unsuitable polarities and corresponding difficulties in mixing. Instead of polarity, Snyder used the solvent strength based on experimentally determined values. This solvent strength results in an additive change of mixing, hence we obtain a mixture of the expected strength. So in evaluating mobile phases, the aim is to find the most suitable solvent or solvent mixture by a systematic procedure, but using as little material or sample as possible and in as short a time as possible. A simple and useful aid in this respect is once again the selectivity triangle according to Snyder. This selectivity triangle makes it possible to virtually compare solvents of different selectivity at one glance. So particularly in the case of unknown mixtures, it is important to compare the separating powers of the solvents from different selectivity groups, but not to forget the optimization of separating conditions and sample solubility. In this slide, you can see 3 plates run with solvents from the different solubility groups. Now, to determine the results of the TLC, following aspects must be understood. The distance of each spot relative to the mobile phase front must be determined. Aim is to have each spot as far away as possible from each other. Moreover, it is important that the spots are all between 0.2 and 0.5 relative to the solvent front. This is a good indication of a suitable interaction with the mobile phase. From the 3 TLC plates, The one with THF showed the best separation results compared to the other solvents, but the RF value, the retention factor, was too high. Hence the spots are also too close to the mobile phase front. Now, since all the spots are nicely separated, all the spots can be slowed down by introducing a breaker solvent, a solvent that slows down the spots and brings all the spots in a better range of the TLC plate, which we learned before is between 0.2 and 0.5. The step with adding the breaker solvent, or the breaker solvent hexane, to the mobile phase is important, as a higher retention factor requires more theoretical plates for the same separation on the column. The calculation in this slide demonstrates this nicely. By not adding the breaker solvents, an 8 times longer column or cartridge would have to be employed to achieve the same separation, and solvent consumption would be also 8 times higher. It is therefore essential to keep the retention factor in the range of 0.2 to 0.5 for efficient separations. So to summarize how to use TLC properly, choose the right solvent according to the Snyder triangle. Aim is to have a good separation between the spots. Adjust the RF values in the range of 0.2 to 0.5 for efficient column separation. If the RF values cannot be achieved, you should try different stationary phases to achieve efficient flash chromatography. With flash chromatography, we can use the advantage that is very difficult to achieve with TLC. We can employ changing gradients over time. This helps separating the individual fractions by adjusting the solvent composition over time. Typically, linear gradients are employed as they are the most efficient, time and solvent-wise. Step gradients are less efficient and are more relics from the open column chromatography time. Now we can talk about the medium impact factor to improve your separations. Efficiency, which is highly dependent on the particle size and geometry of the stationary phase employed. In this slide, you can see a nice example of a spinach extract that was once separated with a flash cartridge with rather larger particle size, and the same separation with a 15 micron particle size column. Both column and cartridge dimensions are more or less the same. What you can nicely see is that the particle size difference has a big impact on the quality of the separation. About or above in the flash separation, the peaks are much broader, hence the time to get the peaks baseline separated is much higher. Below, we have much narrower peaks, which lead to shorter runs to achieve the same goal of baseline separation. The linear flow rate also affects the plate height. The greater the plate height h, the smaller the number of plates n, and hence column efficiency for a column of the given length is. If the Van Diemen curve are calculated for absorbance of various particle sizes, the following picture is obtained that you can see in the slide. The diagram shows that the ascent of the curve with increasing linear flow rate after H0 is substantially flatter in case of small particle sizes than for larger ones. However, a slow flow rate means a long separation time. In practice, therefore, a compromise has to be made between the separation time and the column efficiency. In this diagram, you can see the effect of sample loading regarding the resolution. On the one hand, the amount of sample has a negative effect on the resolution. You can imagine this, that the stationary phase gets blocked by the sample and that the compounds running through the cartridge get broader. Now, particle size also has an effect. The smaller the particle size, the higher the loading capacity is. This mostly because the peaks are narrower, making it easier to achieve the target resolution. The downside of smaller particle size is the higher resulting back pressure. Now let's look at this equation to govern back pressure in a packed bed. Pressure is directly proportional to viscosity, column length, and flow rate. In practice, the viscosity of a fluid usually manifests itself as a resistance to flow. So if a high viscosity liquid is used as the HPLC mobile phase, a higher pressure will be observed. This is very often the case with reversed phase mixtures. Water and alcohol mixtures result in pretty high viscosities, leading to very high back pressures. In this diagram, the relation of back pressure and flow rate is shown. Obviously, the higher the flow rate, the higher the back pressure. Now, at a flow rate of 100 ml per minute, it can be nicely seen that the effect that particle size has on the back pressure. For 30 micron particles, the back pressure is 10 bar. For half the particle size, already close to 40 bar. And for 5 micron particle size, over double the back pressure. Now you can see that the hardware needs to be able to withstand these pressures. So plastic cartridges typically have a limit of around 15 to 20 bar. So smaller particles will lead to different hardware to be used. This is why for HPLC, where typically 5 micron particles and smaller are used, metal hardware is required. Spherical particles with a tight particle size distribution can be packed more uniformly into cartridges than irregular particles. Those packings often show channeling or pockets, which causes for brand spreading and a decrease in resolution. Spherical cartridges combine those advantages to provide superior resolution in comparison to irregular silica. And not only the effect can be seen with the resolution, also the loading capacity can be increased and the run times can be reduced. Here an example showing the better resolution. Both runs were done with identical sample and cartridge. The only difference was the particle geometry. And the result is the resolution, which I must admit is not perfect, but is much better with the spherical compared to the irregular one. The diagram shows the resolution obtained as a function of loading for different cartridges. As expected, resolution at the lower loadings is essentially a function of particle size. For higher loadings, the resolution decreases strongly. The optimum loading for an efficient and economical separation of a mixture of substances depends on so many factors, such as the chosen solvent system and gradient and the amount of target compound and the impurities in the sample, and the resolution at lower loading. The better the initial separation, the more sample can be loaded while still obtaining satisfactory separations. For standard separations at medium loadings or less challenging separations at high loadings, bigger particles are the most economical solution. Medium particles such used in our Flash Pure ID cartridges excel at separating challenging samples at low to medium loadings. The Flash Pure Select cartridges provide the best performance for any application due to small and spherical particles, especially for complex separations at high loadings. This material shows highest efficiency. Choosing the right cartridge for your separation problem will help you get most of your chromatography set up and obtain the best cost of benefit ratio in each separation. Now we come to the trade-offs you have to make. It is very, very simple. The better the performance of your cartridge, the higher the price. The order is clear. Spherical is better than irregular, hence more expensive. And smaller particles is better than bigger particles. The combination of small and spherical is the non plus ultra and shows the best performance at the highest price. Now to some tips and tricks. Phase collapse is best described as a de-wetting phenomenon. It can cause a total loss of retention and chromatographic problems such as peak tailing, non-reproducible retention times, and also gradient delays. Reverse phase stationary phases are usually quite hydrophobic, dependent on the link chain length. So to prevent phase collapse, reverse phase columns with C4 to C18 modification should be operated with at least 5% organic content in the mobile phase. Another tip is the Silica. Silica gel has a very high specific surface area. This is around 800 square meters per gram. And this allows it to absorb water very easily, making it also a very useful drying agent. So silica gel is often described as absorbing moisture, which may be appropriate when the silica gel's microscopic structure is ignored, as in silica gel packs or other products. However, silica gel removes moisture by absorption onto the surface of its numerous pores rather than absorbing into the bulk of the gel. If this happens in your flash cartridge, you will have a negative impact in your separation performance. So, important rule, keep your cartridges in a dry place and keep the lids on. One for equilibration and conditioning. This stage is very crucial to achieve the maximum performance of your column. It activates the silica and removes the air from the cartridge. For optimum purification, this step must be performed prior to sample loading. So rinse the column with 3 to 5 column volumes depending on the phase and column size. Generally, the solvent or solvent mixture for this step is the one used at the beginning of the purification. And for the storage after use, normal phase silica cartridges are single-use columns and should not be stored or reused. If this is, however, desired, then I recommend 100% isopropanol. For the bonded phases, C18, diol, amino, it is advised to use an alcohol mixed with some water. So the take-home message for you today is selectivity is the most powerful way to improve your separations, but it is time-consuming and resource-intensive. Efficiency is a bit less performant, but gives easy and quick results. So if you're using automated flash chromatography, you are on the best way to reach your goals easily. Thank you very much for listening. I will be available here to answer some questions in the chat. The questions that I won't answer during this webinar, I will try to answer in the coming days. And beforehand, we also got some questions in that I would like to answer now. So the first one is, which factors affect the resolution when scaling up from a 150 to a 3.8 kilogram column? The logical approach here is to increase the flash cartridge or column size. So there are many factors that here have to be accounted for. One is the cartridge size, the loading is also different, gradient, and the flow rate. And if you know what to watch out for, it is fairly straightforward. So for the cartridge, a good rule of thumb is 10% of the silica weight can be used as sample loading. That would be 1 gram on a 10-gram cartridge, or 10 grams on a 100-gram cartridge. Obviously, if due to the sample loading, the loading is higher or lower, this will also be seen, this effect will also be seen on a larger cartridge. And what also will happen if you go on larger columns is that your sample will get larger. So with a 3.8 kilogram cartridge, you will most probably not be able to load with a syringe. So you'll have to probably go for a sampling pump or something like that. Now, a cool thing is when you work out gradient in column volumes mode, you have the advantage that the flow rate does not affect the shape of your gradient. So you can use the identical gradient for a small cartridge as for a large cartridge. You only have to adapt the flow rate parameter for the cartridge. And this flow rate is typically default for a cartridge. And this is adjusted to have an equal linear flow. So at the end, you don't need to worry about the diameter or the length of the cartridge. Then to the second question, what about starch? The most common stationary phase is obviously silica, as I mentioned in the webinar, but also starch is a good material to be used as a stationary phase, just due to the chemical properties. But starch as a stationary phase is slightly more difficult to handle than silica because you have to pack the columns yourself. Also starch, well, because obviously you cannot buy pre-packed starch columns. And also the starch, when it's wet, behaves different to silica. So here, the higher the flow rate, the resulting higher pressure will cause for a blocking of the flow and also an expansion of the stationary phase bed. And this makes it difficult to work with high flow rates, and it also requires special columns. And these columns are mostly, they're called plunger columns, and they can handle the expansion of the bed. The third question is it possible to separate very closely spots by your system for biomolecules like peptides? So the best way for peptides is reverse phase chromatography. For the easiest ones, just normal C18. There we get many standard pre-packed cartridges that can do the job. If the molecules get bigger, the peptides get bigger, it is worth to go for the C18 wide pore, which enable better retention for the larger molecules, because these larger molecules fit inside the pores and therefore have better retention. And if they're really close together, there is no way around of using a prep HPL or prep pure HPLC column, preparative HPLC columns for these separations. And here we go for C8 or C4 stationary phases, as they typically have better performance for larger molecules. And then fourth question is, what is end capping and what is the advantage and disadvantage? So if you imagine a silica particle, you have this huge surface with the silanol groups, and you modify it with C18 chains. These C18 chains are really long and large, and these chains do not cover the whole silica surface. That means in between these chains, there are still some silanol groups that are free, and they are obviously very polar. Now, what you can do is end capping, and end capping is basically modifying the silica again, just instead of C18 using smaller groups, smaller C groups, just to block these additional spaces on the silica surface. And that means the advantage of end capped substances is the polar is the surface is more unpolar, which gives better separation in many cases, because you don't have any sticking of compounds on the surface. And final question here is, how many times can I reuse a C18 column, and what can I do to extend the life of these columns? So with the C18 columns, I always imagine them being like a silica gel wrapped in a raincoat. So water that goes on this surface just pearls off, or solvent that goes on this surface just pearls off and doesn't stick on these on the stationary phase. And this makes it very very durable, so they can be used multiple times. I have seen already, or typically we say they can be used 10 times, 10, maybe 20 times, but I've seen some people use them over 100 times, because they really, really look after them. They wash them after every use, and they always keep them nice and wet. And you can do this really by just purging them with some solvent after each run, and storing them in an alcohol water-based mixture, so it doesn't run dry. And if you do that, you can keep these columns for a really long time. Okay, so these were the questions that came in before the webinar. Now I'd like to answer a few questions that came in during the webinar. I'll quickly scroll through some. So I've got one question on solid loading. If it is beneficial to load the sample on an inverse media, example, loading a C18 when using normal phase silica and vice versa. Could this result in a smaller band? So we generally do not recommend doing this, just because you very often run the risk. Let's say you have a C18 column and you load your compound on the normal phase silica. There you just run the risk that the compounds stick too much on the silica, because obviously they're also very polar. So they might stick on the silica and you won't be able to get rid of them. So we always recommend to use the same media for the solid loading. And then I've got a question here about an ethyl acetate fraction from a plant extract. What do you suggest me to separate the compound from the ethyl acetate fraction? So here, if it's an ethyl acetate fraction, I would try a normal, a TLC with normal phase, see how the separation works. Ethyl acetate and hexane work quite well, and most probably you'll get a good separation out of that. Okay, so the other questions I will try to answer via email in the next few days. And if you have any other questions that pop up later on, you've got myself as a contact person, you've got my email, and our sales manager for Germany and Benelux, Martin Verstegen, which you can contact at any time if you have any questions. Also, we're happy to receive any samples for feasibility studies, so we can try out on our instruments. And yeah, so thank you very much for your attention, and see you another time. Goodbye.